Okay, class. Now we look on the properties of the magnetic materials. Okay, so the magnetic properties are related to the atomic structure. So which each atom of the substance, okay, for example, produce a tiny atomic level magnetic fields because it moving electron constitute and at atomic level currents and current create magnetic fields. Okay, so for the non-magnetic materials, okay, so these fields are randomly oriented and cancel. However, for the ferromagnetic materials, the field in small region, so called the domains, which cannot be cancelled. Okay, so if you refer, okay, so this is the domains. Okay, so the ferromagnetics, okay, region cannot be cancelled. Okay, so if the domain fields of the ferromagnetics line up, okay, the material is magnetized. Okay, so if they are randomly oriented, okay, so the material is not magnetized. Okay, so on the magnetizing specimen. Okay, so a non-magnetized specimen can be magnetized by making its domain fields line up. Okay, so the following figure, okay, show how this can be done. Okay, so as current through the coils is increased, okay, the field strength increases and more domains align themselves in the direction of the field. So we can see here, okay, so initially A is randomly oriented. Okay, so as the current increase, so the field strength also increase. Okay, so more domains now are aligned themselves. Okay, as I pointed here in the graph. Okay, so the progressive change in the domain orientation as the field is increased. So H is proportional to the currents. Okay, so now if the field is made strong enough, okay, almost all domain fields are lined up and the material is said to be the saturation and almost flat portion of the VH curve. Okay, so at the saturation, okay, at the saturation levels, okay, so we can see, okay, the almost flat portion at the pH curve. So this is the saturation value where the field is made strong enough. Okay, so in saturation, the flux density of B increase slowly as the magnetization intensity H increase. Okay, and then this means that once of the material is in saturation, that you cannot magnetize it much further, no matter how hard you try. Okay, so it's saturated. Okay, so and the saturation value is depends on the materials used for the magnetization circuits. Okay, so flat zero, okay, a trace from the non-magnetized state to the saturation state is termed in the DC curve or the normal magnetization curve. So this is the part, right? Okay, so this is the normal magnetization curve. Okay, from the non-magnetized state here, okay, until the saturation state. Okay, so the hysteresis. Okay, what is the hysteresis? Okay, so hysteresis is actually characteristic of the magnetic materials. Okay, so it present by H. Okay, so H can be readily increased or decreased by varying the current through the coil of the wire. Okay, and it also can be reversed by reversing the polarity across the coil. Okay, so the hysteresis curve illustrate the development of the hysteresis curve. Okay, so let's start. Okay, by assuming the magnetic core, okay, unmagnetized, so that your B, okay, this is when your magnetic core is unmagnetized, where your B is equal to 0. Okay, and then your H now is increased from 0. Okay, and then the B also increased proportionally, okay, as indicated by the curve in figure below, figure A below. Okay, and then, okay, when the H reach a certain value, okay, the H here reach a certain value, Okay, the B begins to level off. Okay, H increase until the B begins to level off. Okay, H increase and the B is follow to increase until the H at certain value, the H reaches the saturation value. Okay, and the B reach a saturation value when the H also reach a saturation value. That's what this page in this figure here. Okay, once saturation is reached, okay, the further increase in H will not increase B anymore. Okay, at this saturation point, okay, the further increase of this H, okay, will not influence the increment of your B. Yeah. All right. So if H is decreased to 0, okay, now if your H is decreased to 0 from the saturation, okay, it will decrease to 0, and B will fall back along the different path. Okay, the B is fall back at the different path to the residual value of PR. Okay, so from here, for the saturation, okay, when the H is decrease to 0, the B also fall back but at different path. Okay, so this indicates that the material continues to be magnetized even the H is removed. Okay, when the intensity is removed, okay, the B is continues to magnetize. Okay, so the ability of the material while magnetized to remain to the magnetized state without the presence of H is called the renditivity. Okay, so this renditivity, also known as the ability of the substance to retain or resist magnetization. Okay, even though your H now is 0. Okay, so your B is still here, but at different paths. Go to the residual B. Okay, so the renditivity of the material is indicated by the ratio of the residual value of B to the B saturation. Okay, so the reversals of the magnetizing force is represented by negative value of H, and achieved by reversing the currents in the coil of the wire. Okay, so we see, when the reversing of the coil, or the reversal of the magnetic force, so an increment of H in the negative direction, so just now, we do at the positive direction, so now we look on the negative direction of H, so the increment in H in the negative direction causes saturation to occur at the value of minus saturation. The same as the positive, the H saturation also happen in the negative direction of H. And the flux density is at the maximum negative value here. The positive side is up there here. The negative side will be the bottom of B. So this is the maximum negative of B. And the negative portion or negative direction of H. And now, when the H is removed again, the flux density B goes to the negative residual, the flux density of B, from here, it goes to the negative residual of value of minus BR. So from this negative BR value, the flux density follows the curve indicates in part F back to its maximum value when the H saturation in the positive direction. So now the H saturation is repeat to the negative, positive value direction again. So this flux density we follow, okay, back to 8 maximum positive value. Okay. So the complete pH curve, okay, in the figure below is called the hysteresis curve. Okay. Right. So material, okay, with the low resistivity do not retain the magnetic field very well, while those with the higher resisttivities exhibit okay, values for the VR very close to the B saturation. Okay. So we know that okay, the high resisttivities okay, will give you the VR very close to the residual okay, B very close to the B saturation. Okay. Depending on the application, the resistivity of the magnetic material can be advantage or disadvantage. Okay, so in permanent magnets and memory cores, the high resistivity is required. Okay. However, in AC motor, the resistivity is undesirable because the residual magnetic field must be overcome each time of the current reverses. Thus, it's relating the energy. Okay. So about the demagnetizing process. Okay. So as indicated previously, simple turning the current off does not demagnetize ferromagnetic materials. Okay. So to demagnetize it, you must successively decrease its hysteresis loop to 0 as in the following figure. Okay. So you have to successively decrease the hysteresis loop to 0. So placing the specimen inside the coil is driven by variable AC source and gradually decrease the coil current to 0. Or you can use the fixed AC supply and gradually withdraw the specimen from the fields in order to demagnetize the circuits. Okay, so the last one, okay, is about the measurement of magnetic fields. Okay, so instrument for the measuring magnetic field or H are known as a Hall effect Gauss meter. Okay, to measure the magnetic field with a such a meter, so we just insert the probe into the field perpendicular to the field, as illustrated in the following figure. Okay, so the meter will indicate the flux density directly. Okay, so we can now measure the magnetic field value. Okay, so with that, I thank you.